All right. So last time in part one of this, we talked about additive color mixing. In additive color mixing, red, green, and blue are the primary colors. Primary colors means those are the colors that you can use to create any other color. Um, and magenta, yellow, and cyan are the secondary colors. Okay, because those are the first colors you create when you mix those three colors together. Now that's when you're mixing light. When you're mixing paint or dyes or ink, the rules are different. And that's because a pigment is not emitting or releasing light. A pigment is absorbing light. So these rules you're probably a little bit more familiar with, except you may have been taught this incorrectly in elementary school. So if you were taught that red, yellow, and blue were the primary colors in elementary school, that is actually incorrect. That is what we thought it was a long time ago, and just through virtue of tradition, we've kind of kept teaching it that way, but that is actually wrong. And that's why your printer doesn't have red, blue, and yellow. It has cyan, magenta, and yellow. So if I start with, say we're going to mix cyan and yellow, you can already see what the answer is, but I want to explain why. Cyan is something that is absorbing red light because cyan is a combination of green and blue. So if you have a cyan paint or dye, it reflects green and it reflects blue. So green and blue light both end up in your eye and it looks like it's cyan. And red light gets absorbed. So if I shine it with a white light, the red light gets absorbed and only the green and the blue reflect into my eyes. Okay. And then yellow is a combination of red and green. So that means it's absorbing blue. Okay. So the cyan took out the red and the yellow took out the blue. And if I mix those together, red and blue have both been taken out and I'm only left over with green. So if I mix those two, I've taken out an extra color and I'm only left with green. So green is absorbing red, it's absorbing blue, and it's reflecting green, and that's why you see that. All right. I could do this again with cyan and magenta. So this is cyan, this is magenta. Cyan takes out the red, magenta takes out the green, and then that combination takes out the red and the green, so you're only left with blue. If you mix all three primary colors, cyan, magenta, and yellow are the primary colors of subtractive color mixing, or the primary colors of pigments, you take out the red, the green, and the blue, and you're left with nothing, right? So if nothing is being reflected and everything is being absorbed, that's when you see black, okay? And your printer's a little obnoxious in that if you run out of black ink, it oftentimes won't let you print because it's like, you need black. But technically, it could recreate black. It won't exactly line up. And so you can sometimes see streaks of color if it tries to create black from the colors. But overall, it works pretty well. Okay, works pretty well. Perfect world, it would be black. All right. So going back, just for one moment here, with subtractive color mixing, the more colors you mix together, the more colors you've taken out, and so it gets closer and closer to black. Whereas with additive color mixing, the more colors you add, the closer and closer it gets to white because you're adding more colors in. So that's why it's called additive color mixing. And this is subtractive color mixing because you're taking colors out. Okay. All right. So how, like in terms of what color is an object, I explained this briefly before, but what's happening is that the cones on your eyes are sending your brain 3 different images. So if there's an object that reflects red light, the red cones send a red image to your brain. And then it sends a green image and a blue image, and your brain kind of puts that all together and creates a composite image, and that's the thing that you are aware of, okay? So what color an object is depends on which part of the spectrum or which colors it absorbs. If it absorbs it, it means that you can't see it. The object might heat up. And what part of the object it reflects. This is actually a big part of why clothing changes colors at different seasons. So if you wear dark colors, it's absorbing most of the light, and that means you are absorbing that energy, or your clothes are. Your clothes are absorbing that energy, but that helps warm you up a little bit. So if you're wearing black and the sun is hitting your black shirt or whatever, your black sweatshirt, your shirt absorbs that, and that energy heats you up a little bit. Whereas in the summer, we tend to wear paler colors, and that's because they're closer to white, which means they're reflecting most of the light, which keeps you cooler. Okay. There is a little bit of a consequence to this, in that sometimes your brain gets confused. Your brain can't tell the difference between yellow light and a combination of red and green. So if an object is reflecting red and green light, your brain will perceive that as yellow. Or if something is reflecting yellow light, your brain will perceive that as yellow. Okay? And so this leads to some... Let me explain why that is. Okay? So if something is green, it's reflecting green light, and so you've got these 3 cones in your head. The red cone will not react to green, and the blue cone won't react to green. So the green one will fire. Okay, and so your brain is like, oh, the green cone is firing, but nothing else is, so that means this object is green. If you had, say, green and blue light that hits your eye, or a cyan light hits your eye, like something in between, that would cause your green cone to fire and your blue cone to fire. But your red cone's not firing. So your brain's like, hey, since both of those cones are firing, it's probably something in between green and blue, which makes cyan. If your green and red cones are firing, your brain does the same thing. It's like, oh, if green and red are going off, it's going to be something in between, which is yellow. But this is sort of a weird glitch to the way your brain perceives color. If red and blue are activated at the same time, but green is not, your brain will be like, oh, the red is firing and the blue is firing. So that it's probably not red or blue. It's probably something in between. But the thing in between red and blue is green. And but your brain knows that the green cone is not firing. So it's like it can't be green. Green is the only thing it couldn't be. And so your brain makes up a color. And that color is magenta. Magenta is not a real color in the sense that it doesn't have a corresponding frequency or a corresponding wavelength on the visible spectrum. So really, this purple and magenta part isn't actually there. Like the spectrum goes from red to blue in terms of what our eyes can perceive. But when we go a little bit beyond that, our red cone is also firing there. So at high frequencies, the red cone starts firing again. And so when red and blue are both being fired, your brain kind of invents this new color. So magenta is a lie that your brain tells you. It's a color that everyone who has normal vision can see, but it's not actually there in terms of the actual light. Okay, it's just a combination of red and blue. And purple and violet are actually real colors, and they have a wavelength and a frequency, but your brain isn't actually capable of seeing them. For whatever reason, purple and violet activate your red cone as well. And it just means that there's a little bit more blue than red, and that's why you see purple instead of making up that magenta. So I say here that your brain is half lying because the blue light is actually there, but the red is not. So it's half lying. In a normal human trichromatic Trichromatic vision. So trichromatic means that you see 3 colors. Chromatic means color, and tri means 3. This is your full spectrum. We started with this picture. Dogs have only 2 cones, and the spectrum that they can see looks more like this. So they can't really perceive the difference between green and red. It all kind of looks yellowish, and then they've got a blue cone. Okay, so they don't really see things the same way that humans do. There is a mantis shrimp that lives in the ocean that has like 16 cones. So it can probably see millions upon millions of more colors than you or I can. And birds, usually, most birds have 4 cones. So again, they'd be able to see more colors than humans, the way humans can see more colors than, say, dogs. Okay. Color blindness is not usually an inability to totally see color. As you can see down here, the vast minority of people who are colorblind don't see color at all, right? So colorblind usually means that one of your cones is either missing or it's in the wrong place. And so if it's sensitive to the wrong range of frequencies, so you see colors kind of off. You'll see here that one of these types is very similar to a bichromatic vision that, say, like a dog would see. These two, like, you can't tell the difference between red and green. But you have ones where it's like, I can't, you'll notice, like, for most of these, it's like they can't really see red, or there's something wrong with red. And then this one down here, the trinomaly, is the one that's hardest to detect in people because they can almost see every color, but that green is not as bright. If one of these lines looks exactly the same to you as this first one on the top, this normal vision, you might want to get your eyes checked specifically and tell them that you have reason to suspect that you might be colorblind. And colorblind is something, especially if you've got one of these mild forms of colorblindness, is something that is very difficult to realize, to diagnose, because in most vision tests, they're not actually assessing your ability to see color, and most kids learn the ability to be able to tell different colors apart. So that's just something to be aware of. Okay. Now, it also turns out that if you are colorblind, colorblindness is more common in males than it is in females in humans, and that's because it's on the X chromosome, and it's recessive. So because men only have one X chromosome, they either have it or they don't. Whereas women, they will have 2 X chromosomes, so it's less likely that both of them would be colorblind. But if, what we started doing at one point was if boys had a certain type of colorblindness, we realized that they had the wrong directions for one of their cones. So one of their third cone was off. That their mom might have the recipe for 4 different cones, okay? And so we started testing the parents, specifically the mothers of these colorblind boys, and we discovered that approximately 12% of the female population actually has a 4th cone. Now, most of the time, this 8 out of 9 times, this doesn't actually help you, because the 4th cone is just overlapping the red cone so closely that it doesn't actually help you see any other colors. But in 1 out of 9 cases, that 4th cone shifts a little bit, and it's actually between the green and the red. And if that is the case, that woman has tetrachromatic vision, and can see about 100 times as many colors as others. Oops. So we've learned that approximately 1% of the female population can see more colors than everyone else. And just like colorblindness is sometimes not detected until way later in life, tetrachromats often are not identified at all, because there's not, you don't develop the language to identify those other colors the way other people do so. Okay. And yeah, that is everything for this week. I hope you're all doing well. And I did add, so in doing my research and preparing for this, I did find some extra resources. And I've included in the assignment a link to a video that is actually talking about mixing colors from an artist's perspective. She kind of goes on a rant about that elementary school education that's incorrect. And she talks about why we should learn it correctly. But anyway, if you're really into color theory or you are an artist, I highly recommend it because she's explaining the same things more from that perspective rather than from the science perspective. And then if you're more interested in like all these cones and all how that works and where brown comes from, I've added another link on a reading that goes through what colors you can make with different types of color mixing and what colors you can't make and how you would go about doing that and which parts of your eye are affected or which cones are affected by every color. So neither of those things are required, the video or this extended reading. But if you were interested, I did link those for you. I will see you next week. Bye.